Bismillahirrahmanirrahim. This is lecture number 4. It is about time rate of consolidation. In the last lecture, which was lecture number 3, we discussed how to find final or total amount of consolidation settlement, and we did a couple of examples. Time rate of consolidation is also very much important. This lecture number 4 and number 5 would be about time rate of consolidation. These are the contents of the lecture number 3, lecture number 4 and number 5. Just to recall, what is the time rate of consolidation? You see in this slide, on the x-axis you have time in years, on the y-axis you have consolidation settlement, right? And this is the progress of consolidation, and settlement increases, but as the time passes it reduces and reaches to the final consolidation settlement. Delta is C, right? But what amount of consolidation occurs at how much time, when we would reach to this final consolidation settlement, and how many years, or how many years would take a particular amount of consolidation settlement, right? This is the theme of this lecture. Why it is important to find time rate of consolidation? You see, if the design life of your structure is 50 years and your calculation shows that final consolidation settlement occurs after 500 years, right? So why to design your foundation or building for a settlement which would complete in 500 years? Why not to design your foundation or building for amount of settlement which occurs within the design life of the structure, which is 50 years. So that's important to know when the final consolidation settlement is going to complete and occur. And a second use, there are many uses. Second use could be that what is a particular amount of settlement, right, after a particular amount of time. For example, you have this building which is, your calculations show that this building would settle by amount of 3 inches, right? And you say this is huge settlement. So what you do, for example, you placed before the construction of building, you place some fill material on this site, and let this fill material be there. For example, you want that when 1 inch settlement is complete, I have to remove this fill, right? So what you do some calculation and find that how long should I place this fill material so that 1 inch of the settlement is complete, right, under this fill material. When that amount of material here, for example, you calculated 1 inch, and it take for example 6 months, so you let the fill material be there for 6 months and it will undergo 1 inch settlement. Then you remove this fill and reconstruct your building. So definitely the amount of settlement would not be then 3 inches, rather it would be less than 3 inches. So in this connection, let's define what is the degree of consolidation, right? This is represented by UZ, capital UZ. Degree of consolidation actually shows the progress of consolidation in clay layer at a particular depth and at a particular time. You have this clay layer and there is a soil element at depth Z, right? So UZ would tell you that after 1 month, after 2 months, after 1 year, at this depth, how much this element has been consolidated, right? How much this element has consolidated. So this UZ is a function of depth and time. At a particular depth in the layer, at a particular time, UZ would give you how much this point or element has been consolidated, right? So definitely at the start of consolidation UZ would be 0 because there would be no consolidation, and after many years or months, after a long time, that soil element at a particular depth would have been consolidated and UZ would be 100% or equal to 1. So the value of UZ varies from 0 to 1. So at time t is equal to 0, at the start of consolidation UZ is equal to 0, and t is equal to tf after a long time, you may say final time, UZ is equal to 100%, and that is when for a particular delta sigma. Let's represent UZ in terms of void ratio. So UZ is equal to E naught minus E naught minus E1. What is E naught? It is initial void ratio at the start of consolidation. And what is E1? E1 is the void ratio at the end of consolidation. And what is E? E is void ratio at some time t, which its value varies from E naught to E1. So you see at time t is equal to 0, E would be equal to E naught. And if you put this E naught here, you see UZ is equal to 0. It means that at the start of consolidation, when t is equal to 0, the void ratio is equal to E naught and UZ is equal to 0. And when t is equal to tf, E is equal to E1 because E is a variable. So at t is equal to tf, the E value is equal to E1. If you put E is equal to E1 here, this cancel with this, and UZ value is 1 or 100%. Let's represent UZ in terms of effective stress. So we already know a relationship between void ratio and effective stress. This is void ratio and this is effective stress. If we know that the relationship between void ratio and effective stress is not linear, it is non-linear. But if we assume this to be linear, then we say that we can correlate from similarity of triangle void ratio with effective stresses, right? And we can derive this equation UZ is equal to sigma prime minus sigma naught prime, sigma 1 prime minus sigma naught prime. What is sigma naught prime? It is effective overburden pressure at the start of consolidation. And when the consolidation progresses with time, the effective stress increases till it reaches to sigma 1 prime, which is the effective stress at the end of consolidation. And what is sigma prime? It is effective stress at any time t for a particular depth. Its values would vary from sigma naught prime at t is equal to 0 to sigma 1 prime at t is equal to tf. So again we can verify this. At t is equal to 0, sigma prime would be equal to sigma naught prime, right? If you put sigma naught prime here, you see UZ is equal to 0. Similarly, at t is equal to tf, sigma prime would take the value of sigma 1 prime because with time the effective stress increases till it reaches to the final effective stress value. If you put sigma prime is equal to sigma 1 prime here, you see both would cancel and uz would be equal to 100%. So first we represented uz in terms of void ratio, and then we represented uz in terms of effective stress. Again, uz value varies from 0 to 1. Now let's represent uz in terms of excess pore water pressure UE, and it could be shown in terms of UE because UE changes with time. As the consolidation progresses, UE changes with time, and so is uz. So you see sigma 1 prime is equal to sigma naught prime plus UI. You know this relationship, right? With time, sigma naught prime would increase to sigma prime and UI would decrease to UE, right? But the summation would be equal to sigma 1 prime. This you already know, and this is also evident from this graph. You see sigma naught prime is the initial effective stress, sigma 1 prime is the final effective stress, right? The difference between these two is the initial excess pore water pressure. When effective stress increases from sigma naught prime to sigma 1 prime, right, then the remaining excess pore water pressure is equal to UE. So if you put in the previous equation, replace sigma 1 prime and sigma naught prime with the corresponding values of UE and UI, you would get this equation. uz is equal to UI minus UE over UI. UI is the initial excess pore water pressure. UE is the excess pore water pressure at any time t, right? And again you can check at t is equal to 0. UE is equal to UI. Excess pore water pressure would be equal to initial excess pore water pressure. If you put this value here, you see UE is equal to UI, then uz is equal to 0. Similarly, at t is equal to Tf, all of the excess pore water pressure after a long time would have been dissipated and UE is equal to 0. If you put UE 0 here, UI cancel with UI and uz is equal to 100%. So we have represented uz in terms of, first in terms of effective stress, then we represented it in terms of first we represented it in terms of void ratio, then we represented it in terms of effective stress, and then we represented it in terms of excess pore water pressure. What is isochrones? The isochrone actually show you the variation of excess pore water pressure, right? Or the value of isochrone show you the variation of excess pore water pressure for a soil layer at different times. Let me explain it to you. This is a clay layer. It is sandwiched between two sand layers. Sand layers provide free draining boundaries to the clay layer, to the drainage. If you apply there is some increase in total stress, excess pore water pressure would be generated in the clay layer and the drainage would occur towards the free draining boundaries, right? So let's see how excess pore water pressure varies along this clay layer at different times. Here we have U axis, actually this is UE axis, excess pore water pressure. This is UE, okay, and this is depth axis. Depth is measured from the top of the clay layer. Right. So let's at time t is equal to 0, u or E would be equal to ui. So this is ui. All along the depth, the excess pore water pressure is assumed to be uniform and it is equal to ui. You see here the value of ui from 0 to this. All along the depth of the clay layer, you have excess pore water pressure equal to ui. What would happen when the time progresses forward from t is equal to 0? At any time t which is greater than 0, how it's going to vary the excess pore water pressure along the depth? You see, as the time progresses is greater than 0, the excess pore water pressure at the interfaces would drop immediately to 0 because these are free draining boundaries. Right? Here and here it would drop immediately to 0. You see, when time is greater than 0, excess pore water pressure at these two interfaces between clay and sand layer would be 0, and excess pore water pressure would be maximum, would vary about something like parabola, right? And it would be maximum at the center. But of course, even at the center, the excess pore water pressure would be less than the initial excess pore water pressure because some time has passed. Now the question is, why it is maximum at the center? Because you see here the soil part element near the center is away from the interface boundary because the water is drains out from here, from here, from here, right? But the maximum distance is towards the center. That's why excess pore water pressure is maximum at this point. Now, if further time is passed, the excess pore water pressure again would be 0 at the interfaces and it would reduce at all other points. And when final consolidation is 100% and all consolidation occurs after a long time, excess pore water pressure would be 0 all along the depth. So these curves are called isochrones. So this is ux, ue and z profile. We can represent this in terms of degree of consolidation. We can represent these curves in terms of degree of consolidation. How? On the x-axis it is uz and on the y-axis it is z. You see this axis corresponds with the top of the clay layer right here. So at time t is equal to 0, how much would be the consolidation at every point in the clay layer? Of course, no point in the clay layer is consolidated, so it would be 0% consolidation. At t is equal to 0, uz is equal to 0 at every point in the clay layer, right? And after some time, as after 1 hour for example, the consolidation at the interfaces would be 100% because ue is equal to ue is here is 0. ue becomes 0. So uz at these 2 points would be equal to 100%. You see here at the interface ue is equal to 0, uz becomes 1 or 100% at the interface. But within the body of the clay layer, the degree of consolidation at the center would be the least one. So the graph would be like this. At the interfaces, uz is equal to 100% and at the center uz is the minimum one because at the center the soil element is consolidated the least amount. As the time progresses, the degree of consolidation would increase, further increase here, and after a long time all of the clay layer, all elements of the clay layer would have been 100% consolidated, and we reach to the final. So these curves are also called isochrones. This is the same isochrones used on the x-axis, but on the y-axis we have normalized the dimension. Z is equal to Z by D. What is D? You see, what is D? You see, the total thickness we represent by 2D, and half of this is D. What is D? It is the longest drainage path. You see, the longest drainage path for a water particle moving from here to here. So the longest drainage path is D. The total thickness H is equal to 2D, right? So we have represented this y-axis by Z by D. D is this D, right? And Z is a variable. So when Z is equal to 0, okay, Z is equal to 0, which is here, Z by D is equal to 0, right? When Z is equal to D at the center, so D by D is equal to 1. When Z is equal to 2D at the end of the clay layer, okay, Z becomes 2D, 2D by D is equal to 2. So we have normalized the dimension here. 1 represents the center, 2 represents the end, the bottom of the layer, 0 represents the top of the layer, and these are the middle values. And these are the same isochrones. Bismillahirrahmanirrahim. So this is a standard graph for the isochrones that you would use in your solution of your problems. This is again the same thing. This axis is UZ, you see, axis is UZ, and Z axis is Y axis is Z by D. It is written H, but actually it is D. I would correct this in the slides, right? It is Z by D. And these are the isochrones. Instead of T, it is capital T, right? It is a timeless time factor, dimensionless time factor that we would discuss in the coming slides. And these are the isochrones for different time factors. As the time, you see, as the time progresses, the degree of consolidation UZ increases till it reaches to this 100%. Now let's discuss average degree of consolidation, and it is represented by capital U. We discussed UZ, which was degree of consolidation, which gives you the progress of consolidation or percentage of consolidation at a particular depth and a particular time, which is a function of both depth and time. UZ varies at different points for same time, and it varies for the same depth at different times, right? And every degree of consolidation gives you the how much on average a particular soil layer has been consolidated after a particular time. And this is what we generally require in our engineering practice, that for a particular clay layer, after 1 month, after 2 months, after 1 year, after 10 years, how much on average the whole layer has been consolidated on average. So this is called average degree of consolidation. And how we can find this? This is an isochrone, right? You see, this isochrone would come to this this area, you can assume that this is the area which has been consolidated and this is the area that has yet to be consolidated. You see, consolidated is not, you can say it's not consolidated area, but this isochrone with time has passed through this area because it is progressing towards the right side as the consolidation progresses. So this is the area, this is the area of the isochrone that has passed, and this has yet to be covered by this isochrone with time, right? So every degree of consolidation would be equal to this area which has gone through consolidation process. The isochrone has gone through this area A divided by total area. This is area A, this is area B. Total area is equal to A plus B. U is equal to A divided by capital A. So this is how we can find out average degree of consolidation. That would give you consolidation, progress of consolidation on average for the whole layer. And of course, now this U is not a function of depth, rather it is a function of only time. A is equal to A, capital A minus B, right? So we can write instead of A minus B over A, and that is 1 minus B over A, right? Or if in percentage form, U would be equal to 100, 1 minus B by A. So area A is the total area, right? And this B is this area under the parabola. So we can easily find the area within this curve, and if you put it here, you can find the average degree of consolidation for this clay layer after some time, at some time t. Or we can write this U, average degree of consolidation, is equal to 100 minus 100 over total area of the figure that was shown in our previous slide. What is the use of average degree of consolidation, right? So average degree of consolidation, using average degree of consolidation, you can find settlement at any time t if you know the final consolidation settlement. This final consolidation settlement, we did this in our lecture number 3, right? And we would do this U at time t, which is every degree of consolidation, in this lecture number 4. If you multiply this with this, you can find settlement at any time t. For example, the final settlement takes, for example, 100 years, right? And you want the settlement of your foundation after, for example, 30 years. So you find U of t at 30 years, multiply this with this, and you will find the consolidation settlement after 30 years. Now let's derive the Rzahi theory of one-dimensional consolidation, right? And it was his genius that in about less than about a century back, he was able to derive a relationship between excess pore water pressure, and you can find excess pore water pressure at any depth z at any time t numerically, right? So what he proved, actually, this differential equation, it relays excess pore water pressure at any time depth at any time t for a particular soil element at depth z. So in a clay layer, at any point that you pick, you can know how excess pore water pressure would vary with time, right? So this relationship between these three parameters, excess pore water pressure, depth and time, this relationship was first derived by Tarzahi, and it's called Tarzahi theory of one-dimensional consolidation, because we are discussing consolidation only in the vertical direction. As you know that behind any theory there are assumptions, right? So to simplify the equation, the derivation, the scientist makes some assumptions, and then he derive his equation, right? And then he check it with the real life variation and see how much is the deviation of his solution from the real life. So these are the assumption that Tarzahi made for his one-dimensional consolidation. Number one is the soil is homogeneous, because for heterogeneous soil it would be very difficult to derive a simple equation. The soil is fully saturated, so it means any settlement, any consolidation that occurs, it is only due to the drainage of water. The solid particles and water are incompressible. It again signifies the same thing, that any settlement, any compression that occurs is only due to the drainage of water. There is no air, no soil compression, soil particle compression, or compression of the water itself. Compression and flow are one-dimensional, only in the vertical direction. Strains are small. Darcy's law is valid at all hydraulic gradients. And you see, this assumption, we know that Darcy's law deviates at low hydraulic gradients, right? But this is an assumption. The coefficient of permeability and coefficient of volume compressibility remain constant throughout the process. Again, there is question about this assumption, because as the consolidation progresses, the void ratio decreases and the coefficient of permeability would definitely decrease. Similarly, the coefficient of volume compressibility decreases as the consolidation progresses. But for simplicity, it is assumed to be constant, and they are valid because we assume the strains are small. So when the strains are small, the variation is not very significant. Assumption number 8, there is a unique relationship independent of time between void ratio and effective stress. The main drawback of the Tarzahi theory is related to the last assumption. It says that the void ratio and effective stress, stresses, if effective stresses are constant, there would be no change in the void ratio. It says this, but practically the soil doesn't behave like this. Even at constant effective stress, the void ratio changes, right? So the main limitation of his theory lies in number 8. So let's derive Tarzahi theory of one-dimensional consolidation. Remember that we would use 3 tools or 3 steps, main steps, to derive the Tarzahi theory of one-dimensional consolidation. Number 1 is Darcy's law or equation. Number 2, equation of continuity. And number 3, coefficient of volume compressibility MV. Mainly we would use these 3 steps to come up with the derivation of to do the derivation of the Zeit theory of one-dimensional consolidation. So for this, for the derivation, you see this is a clay layer of thickness 2d, and you know that d is the drainage path because the layer is sandwiched between two free draining boundaries. The longest drainage path is the half of this, so the longest drainage path is equal to d. If we assume a soil element, right, the vertical axis are the z-axis, right, and axis, horizontal axis, you can say this is the x-axis, and the axis perpendicular to the screen is y-axis. So the area of this element is dx into dy. Its dimensions are dx dy by dz. This element, it is located at depth z, and its thickness is equal to dz. So we will focus our attention to this soil element. Vz is the velocity. When there is a change in total stress, there will be excess pore water pressure and water would drain out of this. There will be drainage of water through this soil element. The velocity in the z direction, in the vertical direction, is equal to Vz. And Darcy law says that Vz is equal to K into Iz. Iz is hydraulic gradient in the z direction. K is the permeability of soil in the z direction. Iz, which is hydraulic gradient, is equal to curly H over curly Z. You know that this is the hydraulic gradient. This is the head, energy head. Variation across the element, curly Z, right? So curly H over curly Z is the hydraulic gradient in the Z direction across this soil element. And there is a negative sign. It shows that in the direction of Vz, the hydraulic gradient decreases, and you know the water would flow from high gradient to low gradient, from high gradient to low gradient. So negative sign shows that the hydraulic gradient would decrease, the head would decrease along the direction of the velocity. We know that this head is due to total head is only due to excess pore water pressure. Why there is a flow of water? Because of the excess pore water pressure. So U is equal to gamma of water into H, or H is equal to UE over gamma of water. Now we can replace this H with this and put this equation here, and you would come up with this equation. Vz is equal to minus K over gamma of water curly UE over curly Z. So this was the use of Darcy's equation, and now we would use the continuity equation, the second one. You see, it is the same soil element that we discussed. The area is dx into dy. This is the velocity that enters into the soil element Vz, and this is the velocity that goes out of the velocity of water, pore water that goes out of the soil element. And you see this is Vz, and this is the variation of velocity with respect to this thickness curly Z, right? And dz is the total thickness. So this is the variation that occurs along the thickness of the soil element. So this is the in velocity, this is the out velocity. If you multiply these velocities with the plane area, cross-sectional area, which is dx into dy, So what you would get the discharge or volume enter per unit time into the soil element. You multiply this with dx into dy, right? And volume of water per unit time going out of the soil element. So actually q out minus qn is the change in volume of this soil element. As the water goes out of the soil element, there is a compression, there is a consolidation of the soil element. So q out minus qn is dv by dt, change in volume per unit time. Now you plug in the values of q out and qn in this equation. That will be, and that would reduce to curly vz over curly z dx dy into dz is equal to dv into dt. We know that from the previous slide vz is equal to minus k over gamma of water curly u or curly z. That was the equation that we derived using Darcy's equation. Now you can replace vz here, put the vz here, and you will get this equation. Now we will use the third major equation, that is coefficient of volume compressibility, MV. We know that MV is change of volume per unit original volume per unit change in stress. We can rearrange this, and then delta V would be equal to MV into V naught and delta sigma prime. We know that V naught, original volume of the soil element, is dx into dy into dz. Now if we divide this equation by delta t on both sides, we have delta V over delta t here and delta sigma prime divided by delta t. Because effective stress is a function of time, that's why it is delta sigma prime over delta t. If we assume that delta t is very small, approaches to 0, then it will become dv by dt, and this delta sigma or delta t will become curly sigma prime over curly t. We know that as the effective stress increases with time, excess pore water pressure would decrease with time. So we can write that delta sigma prime over curly sigma prime over curly t is equal to curly effective excess pore water pressure UE over curly t. So as excess pore water pressure decreases with time, with the same amount effective stress would increase, but with a negative sign, because if one commodity is increasing, the other is decreasing. So we can replace in this equation curly sigma prime over curly t with curly UE or curly t with a negative sign. The equation would become like this. Put this equation here, this would be like this. Now the equation of dV by dt is in terms of excess pore water pressure. This is the equation that we derived in our previous slide of dV by dt. It is again in terms of excess pore water pressure, but changes with respect to z. Now we can compare dV by dt in both equations, and we compare it, and you will have this equation derived. And this could be again simplified by Cv is a constant, which is equal to K over sigma gamma of water mv. If you bring mv on the other side, that would become gamma mv over K mv over gamma water, that would become CV. What is CV? It is called coefficient of consolidation and its units are in meter square per year. And this is the differential equation that we were seeking, that we derived. This is called Tarzahi one-dimensional consolidation equation.